Alright, now we are going to just look at a little bit more practice of things that we've already seen, understanding applications, graphs, all that fun stuff. So let's get to it. Alright, I want you to label points A, B, C, D, E, and F on the graph below where you think the following things are true. This is an approximation. There are many correct answers to some of these, but I want you to try to think about this. So, for instance, point A is a point on the curve where the derivative is negative. So this is the function. Where is the derivative negative? So I want you to pause the video and label points where these would be true. Unpause when you are ready to check. Alright, so this is what I came up with. Again, these are, some of these, like A, I just gave you ranges of where you should label it, but I didn't give you exact locations because there are many. So again, let's look at these. So point A is a point on the curve where the derivative is negative. If the derivative is negative, what do we know about the function? That means that the function is decreasing. So anywhere in this range, the function is decreasing, and anywhere in this range, the function is decreasing. Part B, point B is a point on the curve where the value of the function is negative. So the only place where the actual function is negative is here. So anywhere on there could be a point B. Point C is a point on the curve where the derivative is largest. Well, the derivative represents the slope of the curve. So where is the slope of the function greatest? And since we're saying largest, we want it to be positive. So the slope is positive here, but it's relatively flat, I guess, or it's not as steep. So we're looking for where is the function the steepest and increasing. So I would say somewhere around here. I mean, again, it doesn't have to be necessarily exactly this point. This is up to your interpretation. But somewhere right around there, I think, is where the function is the steepest, increasing. Therefore, the derivative will have the largest value. Point D is a point on the curve where the derivative is 0. So that's any of these 3 points, because the derivative is going to be 0 when the curve has a relative maximum or minimum, because the horizontal tangent line will be there. And points E and F are points where the curve, on the curve where the derivative is about the same. So if the derivative is about the same, then what we're looking for is the slope of the function to be parallel or the same. So it looks like about right here, if I was to draw a tangent line, and if I draw a tangent line there, that they'll be close. So they'll be about the same. Again, it's up to your interpretation whether it's exactly those points, but that's what we're looking for is if the derivative has the same value, then that means the function has the same slope, i.e. the tangent lines would be parallel. Alright, I want you to try this one. A child inflates a balloon, admires it for a while, and then lets air out at a constant rate. If V of t gives the volume of the balloon at time t, then the graph below represents V prime of t. At what time does the child, and then you are going to answer these questions. So I want you to pause the video, think about this, unpause when you are ready to check. Alright, so when does the child begin to inflate the balloon? Would be right here at 3 seconds, assuming that that's in seconds. And then the balloon is being inflated up until here, where he stops inflating the balloon, or I guess the child. We don't know if it's a he or she, I apologize. So B, right here at 9 seconds, would be when the balloon is finished inflating. When does the child begin to let air out of the balloon? That's going to be here at C. So this is the child letting air out of the balloon, because remember, the thing you want to keep in mind, this graph represents the rate of change of the volume of the balloon. So that's why the volume of the balloon is not changing, it's not changing, it's not changing. Now it's changing. So this would be a rate of change of the rate of change of the volume. But now it is still changing, it's just changing at a constant rate. And then it stops changing. Now we don't do anything. And then we let the air out, so the volume is changing negatively. We let the air out, and then we stop letting air out. So then part D is saying, how would the graph of v prime of t be different if the child had alternated between pinching and releasing the opening of the balloon to release the air? It would look something like this, where you would keep bouncing up and down as you are releasing air, stop releasing air, releasing air, stop releasing air, releasing air, stop releasing air, and so on. All right, next one. Water is flowing into a tank. The depth in feet of the water at time t in hours is h of t. Interpret with units the following statements. So what does h of 5 equals 3 represent? H prime of 5 equals 0.7. H inverse of 5 equals 7. H inverse prime of 5 equals 1.2. So I want you to interpret these in the context of the problem. Again, we talked about this before. Think about the units and also understand that in some of these, it's not going to really make sense what the interpretation is, but it is what the interpretation is. And by make sense, I mean that we wouldn't really think about a problem in the context in this sort of fashion, but that's what these things are sometimes representing. So pause the video, try to do this on your own. Unpause when you're ready to check. Alright, so the first one, if we have h of 5 equals 3, and we know that h of t is the depth in feet of water at time t hours, then I know after 5 hours, the depth is 3 feet, because this represents t, so that's time in hours. This represents depth in feet. Alright, hopefully that one's pretty straightforward. Now let's talk about dh dt. So the derivative is going to be the rate of change of the height at some time t. So if h prime of 5 is 0.7, then we can interpret this as at 5 hours time, the depth is increasing at 0.7 feet per hour. So remember, this is an instantaneous rate of change. So that's what I'm saying, at 5 hours time. Or you could say after 5 hours of time. Either of those would be fine. H inverse of 5 equals 7. Okay, well, what does this mean? Well, remember, inverse functions, we switch the x and the y. So h inverse of t is actually the function t of h. So now the input is h and the output is t. So what does this mean? It means when the depth is 5 feet, it has been 7 hours. Okay? So we switch the variables. What about h inverse prime of 5 equals 1.2? Alright, so now again, the input is height, and now the output is rate of change of time. So this is where it gets a little weird. So, at 5 feet depth, it takes 1.2 hours to increase a foot in depth. Because now, the derivative, so h inverse prime of h, because remember this is a function of h, is dt dh. So now it's the rate of change of time per height. Right? Got to think about that. Now, again, this is what I was talking about. Why would we ever talk about the rate of change of time per height? Like, that doesn't... I can't think of when you would want that relationship as opposed to having how is height changing per time. That's useful. But this is still how we interpret it in the context of the problem. So just because it's not a normal way to interpret something doesn't mean that we can't do it. Okay, so we've seen these before. I want you to sketch a graph of f double prime given the graph of f. Pause the video, try that, unpause when you're ready to check. I will give you a hint. I would recommend sketching f prime first. Alright, now pause. Okay, so I know that if I sketch f prime, I'm going to end up with, okay, where there's a maximum here on the function, the derivative is going to have a 0. Where there's a minimum here on the function, the derivative is going to have a 0. And I know since the function was increasing here, the derivative is positive. The function is decreasing here, so the derivative is negative. And then the function is increasing again, so the derivative is positive. Alright, so the red function, or the red graph, is the first derivative. So now I need to do the second derivative. So I notice, okay, there is a minimum on the second derivative here, so that's going, on the first derivative, so that's going to be a 0 on the second derivative. Because remember, now I want to actually just think about this, the first derivative here is actually, now that's my function, and so the blue graph is the derivative of that. So I follow the same sort of idea. So since there is a relative minimum, that's going to be a 0 on the second derivative. Since the first derivative was decreasing, the second derivative is negative. Since the first derivative is increasing, the second derivative is positive. There you go. All right, our conclusion, same as before.